Hello, this is Mr. Blag, and today we're going to be discussing solving systems of linear equations by substitution. Okay, so we'll jump right in. You know that a system of linear equations is a system of two equations, okay, with two unknowns, an x and a y in each equation, and you're looking for a solution, which we talked about graphically, meant a place where those two lines, whatever they might be, intersect. Okay. And so if we look at this first example, if we're doing something by substitution, that means we're taking some value or expression and we're quote unquote plugging it in somewhere else. Okay. So if I look at both this equation and this equation, is there an instance where I can solve for the x or y variable in either of these equations that's the simplest? And it looks like if I look at the second equation, if I just move this 4x over to the other side, we'll have y all alone. So let's do that. So I'm going to say subtract 4x, subtract 4x. So now for this equation right here, I get y is equal to 24, or let's just write it this way, negative 4x plus 24. So now that I have y in terms of this expression with x, I'm going to take that and I'm going to plug that in where I see y in the other equation. So let's rewrite that other equation. 2x minus 3y, where y is now all of this. So I'm going to say negative 4x plus 24, and that equals negative 2. Okay. Nope. So notice all I've done is rearranged that second equation. I got y all alone, and I took that expression, okay, and I plugged it in to the first equation where I saw y. And that's what all this is. So let's go ahead and simplify that. We get 2x. Now we're going to distribute this, okay. That's going to be plus 12x minus, what's 3 times 24? Negative 3 times 24, that's negative 72, equals negative 2. Okay. Now that's going to get me 14x equals, let's go ahead and add the 72, add the 72. We get a result of positive 70. Now divide both sides by 14, and x should equal 5. Okay, so x equals 5, but when we're solving a system, okay, we need an x value and a y value. Okay, because like we said, if we're talking about graphically, a solution to a system of two equations is actually some coordinate pair, ordered pair, x comma y. So now I have x. So I'm going to go back to the expression that had y all alone, and I'm just going to substitute in my x value. So y equals negative 4 times 5 plus 24. Now we could have used any equation, okay, the first or second equation we were originally given, or that equation that I created by rearranging and getting y alone. And I chose that one because that already had y all alone. Okay, so y is equal to negative 24 plus 24. So y is equal to 4. Okay. Now that I have x and y, I'm going to go ahead and say that the solution is the ordered pair 5, 4. There's my final answer. Okay. And that was by substitution, because all we did is we rearranged that second equation to get y all alone, and we took the expression, okay, that we made, and we plugged it into or substituted it into the first equation where we saw y. And then it was just a bunch of algebraic simplification that we solved for the x variable, okay? And once we got that, we could go and substitute that back in and find the y variable. So let's try another one. So solve the system by substitution. Okay? Let's take a look at this. We're going to do the same procedure, but I chose these next two examples to show us some possibilities of what might happen, different scenarios for answers. Okay, so if we look at this, okay, I'm going to go ahead and say that this second equation appears to have the variable y isolated, and if we just move, let me just put it in the same bubble, just so we're using the same system. If we move that 3x over to the other side, we'll get a similar situation where y is equal to negative 3x plus 18. So this, okay, will be what I'm substituting in where I see y. So I'm going to rewrite that first equation, 2 times y, where y now is this expression with x in it, negative 3x plus 18, plus 6x equals 36. So what I did so far, to recap, is I rearranged the second equation they gave me to get y all alone, and that expression was in terms of x. Okay, I took that expression, okay, that was equal to y, and I plugged it into, or substituted it into, where I saw y in the first equation. Okay. Now you can use either equation to isolate for y. I just choose the one that has the smallest coefficient in front of a y. Or the x. It just really doesn't matter. When you're solving by substitution, you want to isolate either variable and plug it into the other equation. All right, so now that I have this down here, let's go ahead and simplify. Let's distribute. We get negative 6x plus 36 plus 6x equals 36. Now it appears these cancel out, and we're left with 36 equals 36. Okay? You're like, what? What do we do with that? Where's our variable? Well, what happens, okay, when we get this, a true statement, 36 does in fact equal 36 all the time. When you get an always true statement and you're solving systems of linear equations, okay, 2 linear equations, that means that graphically what's happening, okay, is you had some line, and then you had some other line that was actually the same line. It was just the formula or the equation of the line looked a little different, okay, but they were in fact the same line. And if you go back and look at those 2 equations, it turns out that if you were to divide that first equation by 2, or multiply that second equation by 2, you would get the other equation. Okay, so they're in fact the same thing. They're in fact the same equation. So this is an example of what we call, when we get a true statement down here, we say infinitely many solutions. Infinite number of solutions. Why? Well, because a solution is the point at which two lines intersect, and if the 2 lines are in fact the same line, then they intersect along the line itself at infinite points. Okay. All right, let's try another example. It's our final example. Again, we're going to solve by substitution. It's a system of 2 linear equations, 2 variables. We'll have a similar procedure, but we'll get a different result, a different kind of answer. There's another possible answer we can get when solving these type of problems. So if I look at this, okay, neither equation is particularly easier than the other to start solving for like one of the variables. Okay, you'll get fractions no matter what. So I'll just choose the first one. Okay, so let's choose the first one. Let's rewrite it. So it's out to the side. 7x plus 2y equals 16. Okay, so I'm just going to solve for y all alone again, because we've already been doing that. So I get 2y equals negative 7x plus 16. Now to get y all alone, I'm going to divide off the coefficient. I get y equals negative 7 halves x plus, what's 16 divided by 2? That's 8. Okay. So now that I have y in terms of some expression with x, okay, if I were to plug this back into the same equation I just used to get that, I'd get a true statement, but that doesn't help me much. So when you're doing this, make sure you take that variable and you plug it into the other equation that you hadn't yet used. And so if I do that, I'm going to rewrite that second equation as negative 21x, okay, minus 6 times y, where y is now all this stuff right here. Okay, so that's negative 7 halves x plus 8, and that equals 24. Okay. So after simplifying, I get negative 21x. Okay. Negative 6 times negative 7 over 2 is, let's see, that's going to be positive 21x. Negative 6 times 8 is negative 48. And that all equals 24. Looks like those two terms with x cancel out, and we're left with negative 48 supposedly equal to 24. Okay. Now when this happens, when you get an untrue statement, okay, when you get an untrue statement, and you're solving the system of linear equations like we have been, okay, then what you say is that there is no solution to this system of equations. And graphically, what that means, okay, we might have already seen this, is that these lines never intersect because, in fact, they're somehow parallel in the xy coordinate plane. And of course, if you have two lines that are parallel and they're not the same line, they don't ever intersect. That's by definition. That's what parallel is. Okay. All right. So if you get an untrue statement, as is the case here, then make sure you understand that that's no solution. So we discussed solving by substitution, where there's a couple different possibilities. One single discrete intersection point, and that's given as an ordered pair, an x comma y value. We also, if we solve by substitution, we might get all or infinite number of solutions, okay, when we isolate the variables and we end up just getting a true statement, as was the case in that second one. And the third possibility when solving by substitution is you have no solution, and that's graphically the case when the two lines that you're trying to solve for a solution for are parallel to each other. Okay, so that completes our video notes 10 on solving systems of linear equations with two variables by substitution. Okay, so by now you should have been introduced to solving systems by graphing, by substitution, and next time we will discuss solving by a process called elimination. Thanks so much. Have a good day.